So students, in this session, let us understand the experimental method to determine the wavelength of a semiconductor laser. Laser, highly monochromatic, coherent, amplified, concentrated beam of light emitting by source. You know this one. Okay, this is highly concentrated. Even you can see in the sunlight. Then meaning of laser is light amplification by stimulated emission of radiation. So there are three processes takes place in case of any material while emission of light. One is induced absorption, spontaneous emission, and stimulated emission. In induced, usually any material contains one ground state and excited state. So a solid, liquid, and the gas as well. Normally, in normal case, at 0 Kelvin, normal electrons are in ground state. When certain energy is applied to the material, electrons goes to excited state, higher state. So this process is called induced absorption. In lasing materials also, what happens? So that by the application of light or any energy, electrons in ground state goes to the excited state of the lasing material. Then electron will not stay for a long time there. Immediately it come back, spontaneously it come back to its original ground state. So this process is called spontaneous emission. Emission means what it emits? It emits the light. So that in figure you are seeing, the first diagram is induced absorption. The diagram is spontaneous emission. First, it absorbs the incident light, incident photon. It go to the excited state. Again, it come back to the original state, ground state, by the emission of the electromagnetic radiation. In normal light, so is by spontaneous emission. In stimulated emission, what happens? By the application of the incident photon, electron go to the excited state. But when electron in excited state, it again absorb another photon, another quanta of energy. In third diagram it is shown when electron come back to the ground state by the emission of two radiations, those having equal wavelength, same wavelength, and those two are in phase. And these are called coherent radiations. Okay, the radiations which having same wavelength are called coherent radiations. Two coherent radiations are emitted. Then how the amplification takes place here? When two coherent radiations in phase, they constructively interfere so that the resultant wave is amplified. Its intensity is increased. Understood? So like this amplification of light takes place. In normal case, in normal material, at that time we get large number of photon with same wavelength. Those are in phase coming out of the material, okay, lasing material, so that the amplification is very high. But in two-level process, the material which contains only ground state and excited state, in such cases, it is difficult to get the stimulated emission, or it is difficult to get coherent radiations, because so that electron cannot stay long time. It is spontaneously come back. There is no chance to electron to interact with the photon in the excited state. So in two-level process, it is difficult to get the stimulated emission. But in case three-level process, yeah, we get the effective stimulated emission. Here you see electron go to the excited state and electron come to the a state in between excited state and ground state called metastable state. Okay, so in meta, why we call metastable? So that partially stable state it is. Electron stay more time means what? Here it is how much? 10 to the power minus 9 in excited state, 10 to the power minus 3 in metastable state. This is very high compared to excited state, 1 millisecond. Okay, so that at that time more and more electron go to the excited state and settle on the metastable state. Okay, within this time, within 1 millisecond, then all the electron at a time come back to the ground state by the emission of the coherent photons, number of coherent photons. Tremendous amplification takes place. Okay, like this in the form of pulse electron. So the photons are the highly amplified photons are emitted. Okay, so this is how the laser will emit. There are 4 level, 5 level lasers are there to get the better stimulated emission, to get the better laser. Okay, so that now we are doing experiment with the semiconductor laser. There are actually 4 types of lasers: solid state laser, gas laser, liquid laser, and semiconductor laser. Okay, so that in solid state laser there are some crystals we are using doped with some other crystal. Gas laser we use the gases, helium neon laser, helium and neons are gases. And liquid dye lasers we use the dyes, liquid dyes. And in case of now semiconductor laser, so we use the direct bandgap semiconductors. Those direct bandgap semiconductors are compound semiconductors. Those are not silicon and germanium. We cannot get the coherent photons in the, so that for electrical circuits we are using silicon and germanium diodes. Those are indirect bandgap semiconductor. So gallium arsenide is direct bandgap semiconductor. Cadmium telluride is direct bandgap semiconductor. Aluminum gallium arsenide is direct bandgap semiconductor. In our semiconductor diode, we use aluminum gallium arsenide. Okay, a direct bandgap semiconductor. So that what happens here is the band diagram of the semiconductor laser. Okay, so that one side this P, so that you know that PN junction you studied already. So P type, you see here a diagram of PN junction is there. This is actually very much small, of the order of 1 millimeter by 1 millimeter by 1 millimeter or less than that. This is very small. Then the P type semiconductor one side which is doped by trivalent material, N type semiconductor other side which is doped by pentavalent material. Okay, so that you know that in N type materials we get excess electrons, in P type materials we get excess holes or positive charges. So when P and N are joined together, okay, sandwiched each other, then we get in between a depletion layer that is called potential barrier. This is also called potential. So the potential, why potential barrier here? Because potential build up at this place. Okay, as soon as you join P and N junction, so that create barriers. That potential which is generated, that will not allow further recombination without application of external energy. Okay, so that external energy means without application of forward bias current. Now you see here in this diagram, one side P type semiconductor is there and the side N type semiconductor is there. Okay, so it is why the diagram is like this. I am not get into that. In semiconductor physics, let us study that one. Okay, so in N type what happens? We have excess electrons, excess free electrons. Those are all in conduction band. Okay, so that in case of P type semiconductor we have excess holes or positively charged particles. Those are in the ground state. Okay, very high in number. When those two are joined, when the circuit is connected to forward bias, means P to the positive of the battery and N is negative of the battery. Then what happens here? So that there is pressure on the electron and holes to move across the border. Border means a potential barrier. Okay, by the application of the forward bias. So these electrons and holes together enters the potential barrier here in potential barrier. Okay, so that then when at that time electron again recombine with the hole, come back to the ground state. So at that time a stimulation starts. If the stimulation start by a photon, then what happens? So that in a very small interval of time, large amount of the stimulation will build up. Coherent radiations will build up. So highly amplified radiation come out of come out from the potential barrier or depletion layer. Okay, so that it's shown here the form of wave light. Like this, we get the light. This is you remember, it is heavily doped direct bandgap semiconductor. It is. Okay, so when the saturation current crosses, means when current is very high, then only we get the laser light. Okay, this is the little explanation about the semiconductor laser. Here we use the phenomena of diffraction to determine the wavelength of laser. Diffraction is the process of deviation of light radiation when it passes through the obstacle or aperture. When light pass, you already know that one. If you pass the light through the head of a pin, okay, so that the sharp edge of the pin. Otherwise, then what happens? You come to know that light is bent or scattering in all directions. That process is called the diffraction of light. Okay. The diffraction is effective when size of the obstacle is comparable with the wavelength of light. Is it? So when the obstacle size or aperture size is comparable to the wavelength with the size is comparable with the wavelength of light, then we get better diffraction. So imagine there is a scale. Then light is incident on the metal scale that contains graduations. The edge of each graduation is almost comparable with the wavelength of light. Same thing we are using here. So I will come to that one. Okay, so that here it is. So only one aperture I have shown you, or light coming and diffraction taking place here. Okay, so this is alternative dark and bright fringes, but it is not. I remember it is not interference. Why interference? In interference, equal fringes are there, equal width, equal intensity fringes are there, but here the fringes having the different intensity go on decreases as we go away from the middle. Okay, middle bright fringe. Why it is like that? Because there are number of sources at small distance. They superpose together. They create a fine geometry. Okay, so that for that purpose intensity go on decreases. Similarly here, when the number of apertures are there, you see how the diffraction taking place from each aperture and light superposed together. Okay, so that here next let us go. This is here we use in our experiment a metal scale, okay, that contains the number of graduations. So that laser is incident on the metal scale, hence the diffraction is taking place when light is scattered from each and every line. Okay, so that here what happens is first order, zeroth order, first order, second order, third order. We are saying this is different. The position of the bright fringe in between this darker one, there is destructive interference. Here constructive. Why there intensity difference? Because at the middle, what happens is the highest intensity. Okay. And then what happens? Little bit destruction takes place here, destructive interference. So, and destructive interference increases, so that intensity go on decreases. Okay. So here, when you remove this scale, what happens? So light directly falls over here. Direct beam. It is shown direct beam. Okay, direct beam. Okay, just you remember this one. So we'll use this one while explaining the experiment. Okay, aim of the experiment is to determine the wavelength of given semiconductor laser by the method of diffraction of laser. okay, at graduation of metal scale. Principle. So diffraction at grazing incidence, that is the principle. What is the when light incident at an angle alpha on the horizontal metal roller, light diffracts from the various graduations at angle alpha, beta, gamma, delta, etc. This is the same, is it right? So that alpha with alpha angle we incident, then we get alpha, beta, gamma like this. So diffraction taking place. And what is grazing incidence? Diffraction of laser at the graduations of metal scale. That is called grazing incidence. The diffraction takes place as shown in figure. I have shown that when bright diffraction spots are due to the superposition of diffracted rays. Bright diffraction spots are due to the constructive superposition here. Okay, different. The distance between consecutive bright spots increases with the decrease in the distance between consecutive graduations. Decreasing. Okay, so that here how it is. So that if the distance between these two graduations decreases, then distance between these two increases. Two consecutive spots increases. Okay, that is inversely proportional. Understood? If it is 1 millimeter, if this much. When we take the half millimeter, the distance between these two become almost double. You remember. Okay, so that way. Okay, so here so the consecutive graduation. This is also called the Vernier division. Okay, distance between two graduations, consecutive graduation is called Vernier division. Alpha is angle between the axis, roller axis, and distance between the point of incidence to the first order diffraction spot. If you see there, you come to know. Okay, so beta is the angle between the roller axis and the distance between point of incidence and second order diffraction. Yeah, I have shown there. Now it will come to that one. In such case, the path difference between any two order of diffraction is given by m lambda is equal to d into cos alpha minus cos beta. Okay, then the value of cos alpha is like this. It is, you should know from, this is from trigonometry. I cannot explain right now here. Alpha square is y square by z, beta square is y1 square divided by z. Then it goes like this, the calculation. Okay, so that this is not much important, just you remember this. Okay, so this is like this. So m lambda is equal to, we get the final equation, this one. Then so rearranging the terms, we get y is equal to d divided by 2z square, y1 square minus y0 square divided by m. This is the final equation. This is for m is equal to 1. When m, what is this? Order of diffraction is 1. Okay, order of diffraction. So y is equal to d divided by 2. In general, we have equation 2 divided by, actually this is y1 square minus y0 square. M is equal to 1. Okay, by mistake it m came here. So in general, same equation. So in general, we have equation lambda is equal to d divided by 2z square, ym square minus y0 square divided by m. Understood? Okay, so that this is m is order. So that now I'll come to explain what is y, what is m, all this. Okay, so that let us understand. Let's go to the diagram again. Here it is, you see. So that, as I said, is a direct beam. There is, okay, there is a board. Okay, here on when light incident on the roller, light get diffracted on a particular board, the light will fall. Okay, so initially this is direct beam. You mark it, the direct beam. There is a board here. On that board, a paper is sticked. On that paper, we get all this, the light fell like this on this. Okay, it is, you see here, this side it is, the actual diagram is given. Okay, so that here x0 is the distance between direct beam and first zeroth order diffraction. This is x0. But what happens for x0, angle is alpha, for direct beam is also alpha here. So for that purpose, this is here, distance x0 is equal to, can be exactly divided into 2. So x0 divided by 2 is equal to y0. Okay, from direct beam to first order x0. If we divide this, we can say this as y0. Okay. Next, what happens from direct beam to the first order x1? Then, so you remove y0, x1 minus y0 is y1, x1 minus y0. Then similarly, from direct beam to second order x2. Then you remove this y0 here, this y0 here. Then x2 minus y0 is y2. So actually, what is here? What are we doing here? We are measuring the distance y0, y1 from the scale to, from the plane of the scale to the first order, second order, third order spots. Okay, y0, y1, y2, y3, like this. See, y0 is x0 by 2, y1 is equal to x1 minus y0, y2 is equal to x2 minus y0, and so on. Okay, so now, so yeah, this is here. This is a procedure same for that. We have a metal roller with millimeter graduations or half graduations fixed perfectly on a plane surface. Take care that roller is not bent. Okay, laser source is kept opposite to a white board. We have one white board. We have to keep the laser source opposite to that at a distance about 2 to 3 meters. The direct light of laser source must fall on the board, so that we should see that keeping the laser source about 2 meter or 3 meter away from the board, and we must see that laser source, laser light should fall at the lower side of the board. Okay, board almost at the center. Now place the surface of with the roller, between the laser source and board in such a way that the laser light should fall on graduations at small angle, so that we should see that the laser is kept. Then what happens? We must see that the laser should pass through the graduations, and like that we should adjust the scale. Yeah, I have shown, so that this is at this place here. Yeah, light is falling and it goes. Initially it was direct beam here. Like this we should adjust. Okay. So now, so we'll come to this. Yeah. Then observe the diffraction spot on the screen. Mark the diffraction spots starting with highest intensity spot and above. Starting with highest intensity spot, we keep on marking. Okay, so that where it is again, it is like this, highest into here. These are not, we should not mark, only here. So from here, it's already marked. We should mark this. Okay, then what happens? So that marks about 10 spots we have to mark. Mark the point of direct spot. After that you have to mark the direct spot, removing the scale. Then measure the distance between direct spot to the all diffraction spots. We have to measure distance. Those are x0, x1, x2, x3, and determine y0 is equal to x0, y2, y1 is equal to x1 minus y0, y2 is equal to x2 minus y0, and so on. Okay, and tabulate the reading. We have to tabulate. How we tabulate? So this is, after tabulating, we have to determine the wavelength using this. So before going to this one, so how we tabulate the reading? Let us see. You see, this is, so that there are some measurements. Soon after the marking the spots on the board, okay, after marking the spots on the board, immediately we have to do one thing without disturbing the setup. You measure the Z. What is Z? Distance between the light where fell on the graduations. Okay, so that almost, so middle point of that light to the board. Light fell on the graduations scale, and little bit distance it take, little width it is. Exactly middle point to the board distance, that is Z. Then vernier division, I have shown that the consecutive distance between two lines on the roller, that is vernier division D, we have to mark, we have to measure. Then serial number, order, 0th order, 1 order, 2, 3, 4, 5, 6, 7 we have to put here, and distance between the direct spot to the diffraction spot x, okay, so that we have to measure, is it right? So direct spot to x0, direct spot to x1, this is the first order, second order, like that we have to measure. Then we calculate y0, y1, y2, like that. M is equal to 0, 1, 2, 3, 4, like that we have to put, okay, so that we have to calculate. Then you take ym square, you calculate, then ym square minus y0 square you measure, and ym square minus y0 square divided by m is the order you have to draw. So here what happens when you come here in these two, the first here you miss the first one, okay, so don't worry about that. Here only, so finally those readings are coming this, okay. Then so after that, so you measure the average of this value, that average of this value gives this ym square minus y0 square divided by m, d divided by 2z square, you have to substitute and calculate the wavelength, okay. So that this is how we are doing the experiment. Now let us take a model here, okay. This is the model, a semiconductor aim, it is written, apparatus is there, okay. Then after that, yeah, you see, you find the diagram I have shown neatly before, so that in this the book the diagram is like this, okay. This is the direct beam. Here instead of x0 they have given y0, y0, y1, y2, that's all, no problem. Then this is a scale. Now, so that let us see how the readings are taken. Yeah, this is the readings, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, like this, and x0, x1, x2, x3, x4, xy, x6, x7, x8, x9, okay. So that this is the x value. Then afterwards y0, y value is calculated, ym, okay, 15, 17, 19, like this you got. Then ym square, you calculate, the student calculated here, you are going to calculate. Then you see here I told to, here you miss, because you calculate y square minus y0 square, okay. So first reading, again y0, m is equal to 0 here, 0, and yeah, this goes 0 here, and you are calculating this, okay. So you calculate ym square, y0 square divided by m, 1 to how much you are taking, 10 or 9, 1 to 9, so that total 9 readings are there. You add all these, okay, all these, so that you added 9 numbers and divided by 9, that gives the average value of ym square minus y0 square divided by m, okay, like this. Then after this, so that what you get the calculation, you see this is your calculated, 10 to the power minus means 1 millimeter, okay. Z1 square is 2.16 meter square, all you should write in meters. 64.34, only if you take 63 point, yeah, its mean is 63.34, okay. It is in centimeter square here, okay, centimeter square, not 4, it's centimeter square, and you make it meter square, that you get 10 to the power minus 4 meter square, 64.34 into 10 to the power meter square. Then if you calculate this one, you get the value, lambda 1 is 6.895 10 to the power minus 7 meter, okay. So lambda 1 is 689. Why lambda 1 here? Because same experiment here, you see the vernier division is 1 millimeter here, you have taken, and there is, he repeated the experiment taking vernier division 0.5 millimeter, Again he repeated the experiment. Okay, here the length is 1.88 meter, is little bit less actually. Okay, no problem. Again you should repeat the experiment like this. You see here what happens. I will show one thing. So 30.5, 32.5, how much is 2 centimeter? Okay, see 46.8 and 49. 46 point almost 47, 47 and 49, right? See almost here also 2. Here also it is 2. It is not possible. If you working with the same laser, so for 1 mm and for 0.5 mm, the same distance will not come. Here 1 mm, if the difference is 2 centimeter, then for 0.5 mm, it is almost, it should be double, 4 centimeter. Here if it is 47, it should come 51 actually. I don't know how it happened here. Okay, so that certainly you will get the wrong value. Okay, wrong value. Here also 2, there also 2. If you take 0.5, actually, so that you are not getting half of the correct value in final answer. Okay, so that here I think, so you check this one, there may be some mistake in calculation. You will not get 686 certainly second value. Okay, so that there is some mistake here. Second one, the first is correct, no problem. Second one is, I think there is some mistake in calculation. Okay, so but finally answer get, I think they have calculated lambda 1 plus lambda 2 divided by 2 means what? So that they have used same laser, and finally final answer it is like this. This is the way we are doing the experiment. Okay, so that now quickly I will show the experimental setup. This is the board. Okay, so that here laser light fell on the board. Okay, a graph sheet is sticked to the board. You see, this is the laser source. Okay, so that from the laser source, see, this is here like this it is. Okay, so that board is that way. Okay, so that I'll come to this place again. This is the surface on which scale is present. Okay, so that I will bring this in the path of light. You see, light in the path of light. I am bringing.